half range Fourier series in arbitrary intervals, right? You see, yesterday we were discussing about Fourier series in arbitrary intervals, right? When we were given a if any function which is defined in uh, some arbitrary interval, like you see, it may be any interval like c comma c plus 2l. When you are given this kind of interval, the length of this interval we are expecting it as 2l. Now, when you are given a 2l length intervals, right, we had seen how to find the Fourier series, correct? If you recall, the Fourier series for this kind of interval, it is f of x is equals to a naught by 2 plus summation an into cos n pi x by l plus summation bn sine n pi x by l. See, this is how, we were writing the Fourier series in an arbitrary interval c comma c plus 2l. Of course, there are some different formulae to calculate these three Fourier coefficients. Now see, we are trying to find out the half range Fourier series. If you recall, we were discussing about half range Fourier series in the interval 0 to pi. I hope you remember this, right? When you were given a half interval, in this half interval, you see, we got, the Fourier series expansion, right? See how we did it by taking the length of this interval, as you see, pi. We extend the actual function into the interval minus pi to pi, right? We extend the actual function in this interval minus pi to pi as either even or odd function. Thereby, you see, we got the Fourier series expansion. In a very similar way, now you will be given a half interval 0 to L, right? You'll be given a half interval, or else you see, I can take it as C to C plus L. I should not speak so, but if you are given some half interval like this, within this half interval, you can find out what you call the half range Fourier series. So to get, you see, what to do to extend the Fourier series, we just extend this function into the other half, minus L to L, so that the given function will become an either even or odd function, and thereby you can write the half range Fourier series. Whatever we did earlier, the same idea we are now using even in the case of arbitrary intervals. See there, we had both half range cosine series as well as half range sine series. I hope you remember that, right? When we were when we were extending it to an even function, we got half range cosine series, and if we extend it to sine series, what you call odd function, then we get half range sine series. So keeping these things in mind, now I'm just giving you the formula for half range Fourier series in arbitrary interval. You see, if this is the story, when you are given a function f of x which is defined in the interval 0 comma l, then we can write the half range Fourier series in two ways. Again, as we discussed earlier, we can write both half range sine series as well as half range cosine series. I hope you remember, when it is half range sine series, it includes only its sine terms, and when it is half range cosine series, it includes only even terms, I mean cosine terms, right? That's how, as you can see here, when it is half range sine series, it is f of x is equals to summation bn into sine n pi x by l. You see, earlier when it was in the interval 0 comma pi, right? When it was in the interval 0 comma pi, how did we write this? You see, f of x is equals to, we have written it like this, summation bn into sine nx, right? In the interval 0 to pi, you see, we have written it like this. But now, since it is an arbitrary interval, you see, instead of nx, we get this particular term here, right? We discussed this yesterday, right? See, we get these things. And now with that term, you see, we need to calculate what you call this Fourier coefficient bn. And you see, earlier when it was this, we used to write it like this. You see, bn is equals to 2 by pi into integration from 0 to pi. How much it is? You see, fx into whatever we have there, sine nx dx. Correct? Now, in a very similar way, when the interval is 0 to L, you see, we are simply replacing pi by L. So that you see, it is 2 by L integration from 0 to L, fx into, that function, whatever is there in the series, we use that function here even in the integrand, sine n pi x by L. Okay, in a very similar way, when you're writing the Fourier cosine series, I mean half range cosine series, see, we write it in cosine terms, a naught by 2 plus an into cos n by x by L. Right? And here again, we can calculate a naught an as we did earlier. In the interval 0 to pi, you see, we will write it as 2 by pi into integration pi, you see. The same way, we are replacing pi here also. We are replacing pi by L. So that you see, we got it as 2 by L into integration from 0 to L fx dx. Right? Then similarly, we can calculate an by this particular formula. Very similar things as we discussed yesterday. Uh, this is simply in the half range, in the half interval. Okay. I just want to mention one point here. You see, the most important thing, somehow you can remember this formula, but the most important thing here is, you see, you may be given a question like this. Find the half range Fourier series. This will be mentioned now clearly. Find the half range Fourier series, for some function f of x in the interval, you will be given it as 0, 2. Right? One point, you see, a similar thing we discussed even in the last concept. There it was, you see, Fourier series for the function, some function f of x, let us say, in a similar interval, you see, 0, 2. Understand, when it was an interval which includes pi, there was a clear distinction. I mean, the interval looks like either 0 to 2 pi or 0 to pi. There was a clear distinction between them. But now here both looks similar. Since there is no pi involved here, you need to distinguish them clearly. Understand, when it is a regular Fourier series, as we discussed last time, when it is a regular Fourier series, we take the length of this interval as 2l. We take the length of this interval as 2l. But when it is mentioned as half range, understand, this length is now only L. Right? We want that interval to be half. Correct? That's how, when it is half range Fourier series, understand, take this length, whatever may be the values there, take that length as L and proceed with that L. When it is a regular Fourier series, when there is nothing about half range, then take the length of this interval as 2l. Though the intervals are same, we should have a clear distinction between them. Looking at the question, we need to identify the correct value for L. Okay, I hope you get this point. Now let me just move on to a question. Right. So you're given one function, you see here, that's a question. You're asked to express the function f of x is equals to x as a half range cosine series. Look at, concentrate on that word, you see, half range. When you are given the function, when you are asked to write the half range series, you need to take this length of interval as L, right? Last time, when it was a regular Fourier series, we took the length of interval as 2L, but now here it should be only L. Now keeping that in mind, you see, I'm just writing all these things. Given f of x is equals to x, right? And the interval of definition is 0, 2. Let L be the length of this interval. Right? Why I'm taking it as L this time? Because the question is to calculate the half range series. Let L be the length of this interval. Therefore, L is equals to the length, 2 minus 0, which is 2. Now the value of L is 2, right? Keep that in mind. Now, therefore, the half range, I'm just writing the formula for convenience. Half range Fourier series, Fourier cosine series. You see, you're asked to write the cosine series. Half range Fourier cosine series in the interval 0, 2 is, I'm just writing it, you see. Don't try to by heart the formula. Try to remember them like this. When it is half range cosine series, we need to write everything in cosine terms. When it is cosine terms, you see, when they are cosine terms, we'll get both a0 as well as an. So we can write like this: f of x is equals to, it is a0 by 2 plus summation an into cos, something like cos nx. But whether we write nx or something else, it depends on the interval you are given. Because here you are given it as arbitrary interval, right? So we should take it as cos n pi x by L. Right? This is the Fourier series. And here, since L is equals to 2, we can also write this as n pi x by 2. Already we have assumed, L is equals to 2. So n by x by L. Or else let us write it like this, right? Where I'm just writing the formula here once, where a naught is equals to, you see, as you have written, as you have seen already, normally for 0 to pi, we write it as 2 by pi. And here you see, we write it like this, 2 by L integration from 0 to L. How much it is then? 0 to L fx into dx. Then an is equals to the same thing, 2 by L into integration from 0 to L, the function, you know, f of x into whatever the function you have in the series, that function has to be considered here. It is cos n pi x by L. Right? So using these formulae, we can calculate both a naught as well as an. Now let me just calculate these two one after the other carefully. Consider a naught is equals to, see, I'm just substituting everything, 2 by, the value of L is also 2, then integration from 0 to 2, then the function f of x you are given is x dx. So it is equals to 2 by 2 is anyway 1, I'm not writing, and then if you integrate x, it is x square by 2 with the limits from 0 to 2. When you substitute the limits, you know, we'll first substitute the upper limit, correct? So for x is equals to 2, we'll get it as 2 square 4 by 2 minus, when you take x is equals to 0, it is simply 0. And that's how you see 4 by 2 means it is 2. Therefore, you know, we got a naught is equals to 2. Let's keep this aside. Now let me calculate an. Consider an is equals to 2 by L. L is again 2, you see, 2 by 2 integration from 0 to 2 fx into this one. Fx is how much? X into cos n pi x divided by 2. See, L is equals to 2, I'm substituting dx. Now see, I'm just evaluating this. 2 by 2 means it is anyway 1. I'm not writing that. And then it's a product of two different functions, and one function is particularly x. So we can use the idea of Leibniz, right? So I'm keeping x as it is. And when you integrate this cos function, you know, we'll get it as sine n pi x by 2 initially. All this divided by, you know, whatever the coefficient you have here for x, that comes in the denominator. You know, here it is n pi by 2. So n pi by 2 comes in the denominator. Looks fine. Then minus, we need to now differentiate this x. When you differentiate x, it is 1. I'm not writing. And we need to integrate the remaining function here. So when you integrate sine, you know, we'll get it as minus cos n pi x by 2 divided by, we'll get one more n pi by 2. Already there is an n pi by 2. And when you take integration, you'll get one more. So you will get here totally n pi by 2 whole square. And you see, in fact, next to this, we need to differentiate this one. But anyway, the remaining are all anyway zeros. So I'm not writing them. So here the limits are only from 0 to 2. Understand, you see, as we are discussing, you know, since many problems, when you substitute the limits, you know, because you have a sine term here, right? Because of that sine term, when you substitute the upper limit x is equals to 2, this 2 will be cancelled out here, correct? 2, when 2 is cancelled, you know, what remains here is only sine n pi, and sine n pi value is 0, right? So you can simply ignore this term for upper limit, and even if you take lower limit x is equals to 0, for lower limit x is equal to 0 also, you know, it becomes a sine 0. When it is sine 0 again, its value is 0. So when you have this sine term, you know, for both upper limit and lower limit, if you check them, you can simply ignore this term. So let me just substitute in only the other term. Now see what happens here. Because of two negative signs, when you multiply them, you will get the product as positive. And moreover, you see, I'm first of all writing the upper limit value. We have actually n pi by 2 whole square in the denominator. Can we take this to the numerator? You see, we can. So we can write it as 4 divided by n square pi square. Right? Now, what remains here is cos n pi x by 2. And here in this, you are substituting x is equals to 2. When you substitute x is equals to 2, what happens here? 2 can be cancelled out, and only the remaining thing is cos n pi. When it is cos n pi, its value is minus 1 to the power of n. So this is what you get for upper limit x is equals to 2. Fine. Let me just write it little. So this is equals to, you will get it as 4 divided by n square pi square into minus 1 to the power of n. Now minus, this minus is to write the lower limit. While writing the lower limit anyway, as we understood already, the first term becomes 0 for sure. And minus into minus, it is plus already. So this minus remains as it is. And now again, the same thing here also, you see, you can take n pi by 2 whole square to the numerator. We'll get this as also 4 divided by n square pi square. And in this remaining term, cos term, if you substitute x is equals to 0, it becomes simply cos 0. The value of cos 0 is anyway 1, right? So no need to write that. What can we do here? You see, we can take 4 by n square pi square common, from these two. So when you take 4 by n square pi square common from that, the remaining things are only this, you see, minus 1 to the power of n minus 1. Now from this, you see, when you get this kind of expression, obviously you should recall, we can take two cases, when n is even and when n is odd. As we know, when n is even, see what happens here. This minus 1 to the power of n becomes plus 1. So that 1 minus 1, the term completely becomes 0. So an is 0. An is 0 when n is even. That's very easy to understand. Then when n is odd, what happens to this? When n is odd, this minus 1 to the power of n, it becomes minus 1. So minus 1, minus 2 into this, 4. So it is minus 8 divided by n square pi square. So this is the value of an when n is odd. Right now, let's just substitute everything into the formula. Therefore, the half range Fourier series f of x is equals to, see, it is a naught by 2. How much we got a naught? You see, it is a naught is 2. So 2 by 2, 1 plus summation. As an exists only for odd numbers, I'm taking n takes values like this. N is equal to 1, 3, 5, and so on. And how much we got? You see, it is 8 by minus 8 by n square pi square into that function cos n pi x divided by the value of L is 2. So this is the half range Fourier cosine series for the function f of x is equals to x in the interval 0, 2. Now see, the function what you are given here is e power x. For this particular function e power x, we need to find out the half range sine series in the interval 0 to 1. Understand the things carefully. I'm just writing all the information what you are given in the question. So you are given, first of all, f of x is equals to x. That's one point. And the interval what you are given is this 0, 1. Okay. Now, since the question is to calculate half range series, as I told you already, take the length of this interval as L. So I'm just taking it like this. You see, let L be the length of that interval. So if you take L as this interval, therefore from that, L is equals to 1 minus 0, which is L is equals to 1. Right. So the value of L is clearly 1. And now if you write the half range Fourier series, half range sine series is, I'm just writing it like this. You see, f of x is equals to, it is summation bn into, it is sine n pi x by L. But it is in arbitrary interval, always we take it like this, sine n pi x by L. Right? Yeah, I'm sorry. The function is not x, you see. This is e power x. Now, see, let me just evaluate these things. Here, what is actually bn, where bn is equals to, it is 2 by L into integration from 0 to L fx into sine n pi x by L. Right? So if you just substitute everything into this, I'm substituting x, L is equals to 1. So it becomes, you see, 2 by 1 integration from 0 to 1 fx. What is fx? You see, it is e power x. Then sine n pi x by 1 dx. Right? We need to integrate now this product. And I hope you recall this formula easily. It's just like, e power ax into sine bx, correct? If you just write that formula, we know integration of e to the power of ax into sine bx. So it is equals to e to the power of ax divided by a square plus b square into, it is this, a sine bx minus b cos bx, right? So we take the formula like this. You see, we need to use now this formula. So it is therefore bn is equals to, you can write it like this, 2 times, 2 into, I'm just taking a little bigger bracket here because we have internal brackets also. Now if you just compare these two, you see a is equivalent to 1 and b sine bx is there, and here it is sine n pi x. The denominator is anyway 1, you see. So b is equals to n pi and a is equals to 1. So if you just substitute those values, see, it is e to the power of x divided by a square means 1 square 1 plus b square means n square pi square, n pi whole square, n square pi square. And now this into a sine bx, a is 1, 1 into sine bx means sine n pi x minus b means n pi, n pi into cos n pi x. The limits are from 0 to 1, right? Now let us just substitute the limits and see how much you'll get. 2 times, see, I'm now first of all substituting the upper limit, x is equals to 1. So even in this exponential function also we should substitute, So it is e to the power of 1, which is e divided by 1 plus n square pi square into, see how much you'll get. When you substitute x is equals to 1, the first term here, it becomes a sine n pi. So that the value of sine n pi, 0. So I'm not writing. In fact, if you want, you can write it as 0 minus n pi into, see, when you take x is equals to 1 here, it becomes cos n pi. So the value of cos n pi is minus 1 to the power of n. So these things, you'll get for upper limit. Next, minus, if you now take lower limit, see here also you should take, right, e power 0. The value of e power 0, as you know, it is 1. So we'll get it as 1 divided by 1 plus n square pi square into, when you take x is equal to 0, anyway it is 0, right? Sine 0, I'm not writing. And here also you see we have actually minus n pi into, when you take x is equal to 0, it becomes cos 0. And the value of cos 0 is anyway 1, right? So that we'll get it as 0 minus n pi. Only this much. I will just simplify this. See, how can we simplify this? Already here is a 2. And can we take anything else common, We can take 1 by 1 plus n square pi square common from all the terms. When you can take, so we'll get it like this, 2 into 1 divided by 1 plus n square pi square, right? This into, what you have there inside, minus n pi e. See, if you look at this carefully, we can also take minus n pi common, Minus n pi can also be taken, you can also bring that out of this. Can we or not? Okay, let me first of all write it and then we'll see whether we can really do that or not. Okay, n pi into e minus 1 to the power of n, then minus into minus, it becomes plus n pi. Right, so now from here, you see, we can also bring, now you can understand, we can easily bring n pi also common from this. So you'll get it like this, you see, 2n pi divided by 1 plus n square pi square into, see, when you take n pi common, I'm writing this term first. So we'll get it as 1 minus e into minus 1 to the power of n. Fine. It is 1 minus e into minus 1 to the power of n. That's a story now, simply. So we have, we got bn as this much. If some of you are interested, we can take n is equals to even or odd. But see, when you take even, when n is either even or odd, you're not getting either of them as zeros, right? When you take n is equals to even, it becomes minus 1 to the power of n becomes plus 1. So that this bn becomes minus 1 minus e. Or, if you take n as odd, it becomes 1 plus e. But you are not getting any term as 0. So it is of no use, right? Let's keep this as it is. Therefore, the half range sine series is fx is equals to summation bn, I'm writing all this, 2n pi divided by 1 plus n square pi square into 1 minus e into minus 1 to the power of n, right? All this is bn, and this multiplied by sine n pi x by l, sine n pi x by l is anyway 1, you see, that's why I'm only writing this much. So this is the series, and if you want you can actually split it into multiple terms, but anyway I'm not interested. Let us just stop here. That's the half range sine series for the function e power x, right? See, that's a question now. You are given the function f of x as x into 2 minus x, and the interval what you are given is 0 to 2, and the question is to calculate what you call the half range cosine series. And after getting that half range cosine series, you're also asked to find the sum of this particular series. See, when you are given this kind of additional question, you should understand you will get such a series, right? See, after getting that half range cosine series or Fourier series, whatever it may be, from that series, you see, when you substitute certain particular value to x, you will get the given series, right? Normally in the half range series or regular Fourier series, we'll get everything in terms of x, correct? But in particular, if you substitute x is equal to some value, you will get a series with only numbers like this. Okay, so keeping the series given in the question, right? Keeping that series in mind, we need to identify the value of x. That's up to us. Okay, we'll also discuss that anyway. Now let me first calculate what you call the half range cosine series for this particular function. See, how can I find out this? If you recall, as we did in the last two problems, the function what you are given is, I'm just writing these things, you see, f of x is equals to, the function you are given is this, x into 2 minus x. That's one point. And can somebody tell me, you see, L? Yes. Here, I'm just writing it for convenience. The value of L, it is equals to 2. Why it is 2? As somebody is saying, since it is half range cosine series, half range series, we take the length of that interval as 2, and the length of that interval is 2 only, right? So that we take the length as L. So here L is clearly equal to 2, and therefore, if you write the half range cosine series, it is how much it is, you see, fx is equals to, because it is a cosine series, it includes only cosine terms, a0 by 2 plus summation an into cos n pi x by L. Fine. So where I'm just calculating these two Fourier coefficients. The first one is a0 is equals to, I'm just writing it like this, you see, 2 by L integration from 0 to L. How much it is then? Fx dx. Then it is equals to 2 by, the value of L is also 2, right? So I'm just substituting L is equals to 2, and here also it is integration from 0 to 2. Then fx, what function you are given, it is x into 2 minus x. See, why should we write this as x into 2 minus x? Shall I multiply them? That will be easy for us, right? Otherwise, you see, for this particular function f of x, it is okay. But while calculating an, we'll again multiply that f of x with cos function. So then it looks like a product of 3 different functions, which I don't require. So I'm just taking this, what you call as, what you say, 2x minus x square. Then, I can easily integrate it, right? So keeping that in mind, I'm just taking it as this, 2x minus x square dx. Now I can easily integrate this. Then it is equals to, if you take 2 by 2, it is 1 anyway. Then if for the remaining things, if I integrate them, 2 into integration of x is, as we know, x square by 2. Or otherwise, if you can write integration of 2x is x square minus integration of x square is x cube by 3, with the limits from 0 to 2. So if you can substitute the limits, so first for upper limit x is equals to 2, we'll get it as x square is equals to 4, minus when you take x is equals to 2, it is 2 cube, 8 by 3. For lower limit 0, both the terms become anyway 0. So I'm just continuing this. So this implies a0 is equal to, see how much you'll get when you take LCM. 3 times 4, 12, 12 minus 8, it is 4 by 3. So the value of a0 is directly what you call 4 by 3. Now let me calculate what you call an. Okay, so and an is equals to 2 by L integration from 0 to L fx into cos n pi x by L. So I'm just substituting everything into this. It is equals to 2 by 2 integration from 0 to 2 fx, I'm just writing the reduced one, 2x minus x square into cos function, cos n pi x by the value of L is 2. So I'm writing it as by 2 into dx. Right. See, now while evaluating this, let us be careful. This is equal to 2 by 2 is anyway 1. I'm not writing. And you see again here, this is also what you call an algebraic expression. Algebraic expression multiplied by something else. So while taking the integration of this product, you see, we can use the idea of Leibniz. So what I can do, you see, 2x minus x square, I'm keeping this as it is. Then when you integrate this cos function, integration of cos function, I hope you remember, it is sine n pi x by 2 divided by, we'll get again n pi by 2. Right? That's one thing. Then minus, we need to differentiate this first function, right? So when you differentiate that, differentiation of 2x is 2 minus differentiation of x square is 2x. Fine. Now we need to integrate this total function. When you integrate that, integration of sine function, now it is minus cos, these things I'm writing there as there. So it is n pi x by 2 divided by, in the denominator, you see, we'll actually get 1 n pi by 2 here, but already there is one more n pi by 2. So when you just multiply them, we'll get it as n pi by 2 whole square. Next, you see, I'll take plus. We need to now differentiate this term. When you differentiate 2, it is actually 0, but there is a 2x minus. When you differentiate 2x, it is minus 2. Now we need to integrate this minus cos and so on. So we'll get it as minus sine n pi x by 2 divided by n pi by 2 whole cube. Right? And now next to this, we need to differentiate this minus 2. And anyway, since its differentiation is 0, we don't continue this and we stop here. The limits are from 0 to 2. Right? Now we need to substitute the limits, right? Look at those terms carefully. We have sine term, in as the first sine function in both the first term as well as the last term. Look at those two functions carefully. When you substitute the upper limit x is equals to 2, it becomes, you see, sine n pi. When it becomes a sine n pi, its value is 0. So we can ignore this term for upper limit. Not only for upper limit, you see, even for lower limit, when you take x is equals to 0, it becomes simply sine 0. So keeping that idea in mind, I'm saying anyway those values, these terms become zeros directly when you substitute the limits, right? Both upper limit as well as the lower limit. We can simply ignore them while substituting the values, right? As you know that, I'm just ignoring it. And now I'm writing the values for upper limit. I'm simply ignoring the first term. Then when you multiply these two minus signs, we'll get the product as a positive 1. And there you see, you're substituting x is equals to 2. When you take x is equals to 2 here, you see how much you'll get. 2 into something went wrong, right? Correct. 2 minus 2 into 2, right? 2 minus 4. So when it is 2 minus 4, its value is minus 2. Then here we have actually n pi by 2 whole square in the denominator. You can take that to the numerator, right? So when you take it to the numerator, it becomes 4 divided by n square pi square. 4 divided by n square pi square. And now here, if you substitute x is equals to 2, it becomes only cos n pi. And the value of cos n pi is minus 1 to the power of n. So this is what you get for the upper limit. The remaining two terms are already zeros. I'm not writing them. Now minus, I'm now taking x is equals to 0. When you take x is equals to 0, see what happens here. 2 minus 0, it is only 2 into, when you take this 2 n pi by 2 whole square to the numerator, it becomes 4 divided by n square pi square. And then when you take x is equals to 0 here, it becomes cos 0. And the value of cos 0 is anyway 1. I'm not writing that also. So what terms can be taken out, you see? We can take a minus common from them, clearly. you can take minus, then 2 into this 4 by n square pi square, everything can be taken out. So I'm just writing it in the next slide. Therefore, an is equals to, you are bringing minus out of that, and then you have actually 2 into 4 by n square pi square, you see. So when you multiply those two, it becomes 8 divided by n square pi square. If you take all this out, we'll get only this much, minus 1 to the power of n plus 1. So it becomes plus because you are bringing both minus signs out of these two terms. Because you are taking minus sign also common, we'll get it as minus 1 to the power of n plus 1. Now you can take, even and odd case. When you take n is equals to even, if you take n as even, this minus 1 to the power of n becomes plus 1. So that it is 1 plus 1, 2, 2 into something you'll get there, right? So that's what I'm writing here. Therefore, an is equals to, when you take n as even, it becomes 2, 2 into 8, 16. So we'll get it as minus 16 divided by n square pi square if n is even. And when n is odd, see what happens, minus 1 to the power of odd number. It is minus 1 plus 1, 0. So we'll get it as 0 if n is odd. So clearly we got the values of a. Now let me just substitute everything into the formula. Therefore, the half range series, half range, let me also write it clearly. Cosine series is, it is f of x is equals to a naught by 2. See how much you got a naught? We got it as 4 by 3. So it is 1 by 2 into 4 by 3, 1 by 2, a naught by 2 plus summation. We should take it as actually an into cos. But see, an exists only for even numbers. That's how we take n is equals to 2, 4, 6, and so on. How much it is? Minus 16 divided by n square pi square into cos. See how much it is? N pi x by L, and the value of L is also 2. So I'm just substituting it, cos n pi x by 2. Now see, this is actually the half range cosine series, but you're also asked to find the value of this series, right? So for getting such a series, I'm just writing, I'm elaborating the series here. I mean, for different values of n, I'm just writing the different terms here. When it is 1 by 2, what is actually f of x? The function what you are given is x into 2 minus x. So it is x square minus 2x. Am I correct? Sorry, 2x minus x square. The function what you are given is 2x minus x square is equals to, see here, if you divide it by 2, we'll get it as 2 by 3. Then see here, I can take some terms common, minus 16 by pi square is actually independent of n. So I'm writing it out of the summation. Minus 16 by pi square into, now I'm taking different values to n. When you take n is equals to 2, we'll get it as 1 by 2 square into, if you take n is equal to 2 here, 2 can be cancelled, we'll get it as cos pi x. Correct? Then plus, if you take n is equal to the next even number 4, if you take n is equals to 4, we'll get it as cos 1 by 4 square into, see here, if you take n is equal to 4, it becomes 4 by 2. When it is 4 by 2, we'll get it as cos 2 pi x. Next, plus, I'm taking n is equal to 6. So we'll get it as 1 by 6 square into, if you take n is equal to 6 here, 6 by 2, it becomes cos 3 pi x, and so on. We'll get terms like this. Probably you can expect the next term, you see, it is 1 by 8 square into cos 4 pi x. Right? So this is what you have, the half range cosine series. Now from this particular expression, we need to write, we need to get these terms. Compare these terms, you see. Do we have 1 by 1 square there? Right? See, first of all, we don't have any 1 square term. Then we have any 1 by 2 square term? No. But we have only even terms, right? Can we take now 1 by 2 square common from all these terms? If we can take 1 by 2 square common, we have certain advantage. Can we take, because they're all even numbers, when you take 2 common from everything, what happens? We'll get odd numbers in the denominator. So keeping that in mind, what I'm trying to do here, the same thing, it is equals to, or else, therefore, 2x minus x square is equals to, there is a 2 by 3, I'm writing it as it is, minus 16 by pi square is there already. But now from all the terms, I'm just trying to bring 1 by 2 square common. Right? 1 by 2 square common from every term. So that what remains there, you see, the first one becomes now 1 by 1 square. Right? When I write 2 as 2 into 1, it is 1 by 1 square into, in fact, it is 1 only, but for convenience, I'm writing it as 1 square. 1 by 1 square into cos pi x plus, when we take 2 square common from the second term, it becomes, 1 by 2 square into cos 2 pi x. Next, plus 1 by 3 square into cos 3 pi x, and so on. Now you see these coefficients, you see, they are exactly similarly as that of, this series, 1 by 1 square, 1 by 2 square, and so on. But moreover, you see, when you look at all these terms, along with this 1 by 1 square, we have a cos pi x. Along with 1 by 2 square, we have cos 2 pi x. Then we have cos 3 pi x. We don't want those terms in the series finally. And moreover, if you look at all the terms in the series, the coefficient of 1 by 1 square is 1, which means we want this cos pi x value to be 1. Then if you look at 1 by 2 square, its coefficient is minus 1, which means the value of cos 2 pi x, we want it to be minus 1. To get either plus 1 or minus 1, we need to see for what values of, those things, for what value of x will get alternately plus 1 and minus 1. We need to see that. Okay. If you remember, when it is cos pi, its value is minus 1. Not only for cos pi, when you have the coefficient of pi as an odd number, I mean cos pi, cos 3 pi, cos 5 pi, they're all negative ones. But when the coefficient is an even number, like cos 2 pi, cos 4 pi, they're all positive values. So for some positive, for some even numbers, you are getting plus 1, and for some odd numbers, you are getting minus 1. Right? However, if you have only either cos pi or cos 2 pi or cos 3 pi, you are getting those values, isn't it? So to get those terms, here I'm simply taking x is equals to 1. Let x is equals to 1. When you take x is equal to 1, you should take x is equal to 1 on both sides. When you take x is equal to 1, see on the left side, we'll get it as 2 minus 1 is equals to, this is 2 by 3 minus 16. We can divide this, you see, 1 by 2 square is 4, 16 by 4 means it is 4 by pi square. What terms you are getting here, you see, 1 by 1 square into cos pi, right? Then plus 1 by 2 square into cos 2 pi, plus 1 by 3 square into cos 3 pi, and so on. If you just substitute all the values, you see 2 pi is 1, and I'm also sending pi by 2 by 3 to the other side. I'm also sending 2 by 3 to the other side, so it becomes 1 by 1 minus 2 by 3 is equals to minus 4 by pi square into, if you just substitute all the values, see how much you'll get. 1 by 1 square. Cos pi value is actually minus 1. So I'm just writing it as minus 1 into 1 divided by 1 square. Then plus cos 2 pi value is actually 1. So it is 1 by 2 square into 1. Then 1, again cos 3 pi value is minus 1. So we have 1 by 3 square and so on. Right? Now see, we want only this series. That too, if you look at the coefficients, the first term has positive coefficient. So I'm just trying to multiply this minus side inside, so that the signs will be changed for every term. And also you see, when you take LCM here, it is 1 minus 2 by 3 means 3 minus 2, 1 by 3. And now see, I'm sending this 4 by pi square also to the other side. So it becomes pi square by 4. And then I'm multiplying all these terms with negative sign. So we'll get it like this. 1 by 1 square minus 1 by 2 square plus 1 by 3 square and so on. Therefore, you see, I'm just writing the final value, 1 by 1 square minus 1 by 2 square plus 1 by 3 square and so on. Sum of these terms is equal to, if you just multiply this, it is pi square by 12. Right? That's the answer. And this is how we'll find out the sum of this series after obtaining the cosine series. Okay.